If only it was always so simple. Welcome to the CBT program on alternative drive systems, which gives you a solid introduction to alternative drives by providing a general overview of this topic. The planet's reserves of crude oil are not infinite. How is our consumption of this fossil resource progressing? Since the turn of the 20th century, the extraction of oil has increased incessantly, interrupted only by the two oil crises. A reversal of this trend is currently emerging. The oil fields which can be easily developed are no longer abundant in oil, while few new oil fields are being discovered. According to the peak oil theory, this means that half of the planet's resources of crude oil have been depleted. At the same time, demand for crude oil continues to grow. On top of this, the process of extracting the remaining oil is becoming increasingly time-consuming. The upshot of all this is increasing oil prices. Crude oil has a whole variety of uses. A large proportion is, for example, used for heating, for the manufacture of pharmaceuticals and chemicals, of which fertilizers amount for a large quantity, for making plastics, and of course, for fuels, petrol, diesel, and kerosene. The global transport sector as a whole represents the largest consumer of crude oil, with around 46% of total consumption. When fossil fuels such as coal, oil, and natural gas are burned, they give off carbon dioxide, or CO2 for short. Although this gas is not toxic, it accumulates in the atmosphere. This has the same effect as the glazing of a greenhouse. Sunlight can enter, but the heat cannot escape. The result of this greenhouse effect is that the Earth's surface, the oceans, and the atmosphere are becoming warmer, something which has predictably dramatic consequences for life on our planet, not just biologically speaking, but in economic and social terms too. However, there is a burgeoning global demand for improved quality of life and especially mobility. This has so far led to a steady increase in CO2 emissions. If you wish to learn more about the CO2 cycle, click on Extra Info. The counter-argument is that humans and animals breathe out carbon dioxide too, and that the gas is also released by decaying plant life. This is indeed correct, but the fact is that the same quantity of carbon dioxide has previously been absorbed by plants through photosynthesis. It forms part of a cycle that has been continuing for thousands of years. The same is true of biofuels, meaning they can be designated nearly CO2 neutral, assuming that cultivation and processing have been carried out in an ecological manner. The decisive factor for climate change is the additional CO2 that is produced by the combustion of fossil substances and upsets this balance. What does the breakdown of CO2 emissions look like? The lion's share can be attributed to the electricity industry, which produces energy in coal-fired power stations. This is followed by industry and domestic households, where heating is needed for manufacturing processes and comfortable living respectively. Transport worldwide, meanwhile, only ranks third for CO2 emissions, with just over 20% of the total. Here you can see the detailed breakdown for the transport sector. Move the cursor over the pie chart to display the various modes of transport. In order to halt climate change, CO2 emissions from all sources have to be cut. In other words, from electricity generation, from industry, from households, and from the transport sector. Politicians are attempting to steer the course of development by imposing general requirements, which vary from region to region. In the European transport sector in particular, CO2 emissions from passenger cars are meant to be reduced to an average of 120 grams of CO2 per kilometre by the year 2012. Daimler AG has pledged its commitment to fulfilling this objective, provided that due consideration is given to the different vehicle classes when calculating the average. Do you want to know what 120 grams per kilometre actually means in terms of the standard consumption figures? Click on Extra Info. Emissions of 120 grams of CO2 per kilometre correspond to a fuel consumption of 5.2 litres of petrol per 100 kilometres, or 4.5 litres of diesel, or 4.4 kilograms of natural gas. 120 grams of CO2 are also released when 1 kilogram of hydrogen is consumed, not from the vehicle itself, however, rather when the hydrogen is produced from natural gas, as is the customary method at the current time. It is a similar story with the power for electric cars. An average of 120 grams of CO2 are released by power stations in Germany, for example, to produce 20 kilowatt-hours of electricity. There are various strategies for reducing CO2 emissions and fuel consumption, which are all being pursued at Daimler AG. Optimization of the vehicles in terms of rolling resistance, aerodynamics, and weight. Optimization of the internal combustion engines. For example, petrol engines with direct injection technology, known as CGI for short, or low-emission Bluetech diesel engines. The development and deployment of alternative fuels such as natural gas, biofuel additives, synthetic fuels, and second-generation biofuel, which can all be used in conventional combustion engines with either little modification or no modification at all. And finally, the development and application of alternative drive systems, such as the hybrid drive, the fuel cell drive, and the electric drive. This CBT program deals exclusively with the latter of these, alternative drive systems. Alternative drives are suitable for reducing fuel consumption, thereby lowering emissions in general, but most importantly, CO2 emissions, and increasingly for harnessing renewable energies too. If you wish to learn about the difference between fossil fuels and renewable energy sources, click on Extra Info. Fossil fuels developed in prehistoric times from plant and animal material. They include crude oil, natural gas, lignite oil, and anthracite coal. Renewable energy sources are derived on an ongoing basis from sunlight. They can be infinitely replenished, i.e. renewed, hence their name. They include not only sunlight itself, but also biomass, wind energy, and hydropower. The only other resources on Earth are primary energy sources, which date back to the creation of the solar system. Radioactivity, for example, in the form of uranium, geothermal energy, as well as the tides, whose origins lie in the movement of the celestial bodies. As the planet's reserves of uranium are limited, they are often counted as a fossil fuel, while geothermal energy and tidal movement are classified as renewable energy sources due to their virtually inexhaustible nature. The following types of alternative drive are to be examined in greater detail: hybrid vehicles, fuel cell vehicles, and electric vehicles. What fuels do these various alternative drives run on? Hybrid vehicles are refueled in the conventional manner with petrol or diesel. Fuel cell vehicles are powered by hydrogen, and electric vehicles run on electricity. However, the whole climate and resources issue has to be considered from a wider perspective, from the original source of energy all the way to the moving wheel. On a hybrid or a conventional petrol or diesel-powered vehicle, the majority of the CO2 release takes place at the vehicle itself. Only a relatively small proportion occurs during extraction and transport of the crude oil and manufacture of the fuel. Although operation of a fuel cell-powered vehicle is emission-free, the overall CO2 balance sheet is not necessarily that much better. Currently, hydrogen is produced from natural gas or accumulates during the smelting of iron ore. Both processes give off CO2, so it is not produced at the vehicle but at the fuel supplier instead. It is a similar story for electric vehicles. Part of the electrical power required comes from coal-fired power stations with relatively high CO2 output. Some of the electricity is also drawn from atomic power and renewable energy sources, which are, however, CO2-free. The balance sheet is far more positive if the electrical power is generated from renewable sources, such as the sun, wind, and water. In other words, without any release of CO2. And if this electrical power is used to generate hydrogen by the electrolysis of water, the overall CO2 balance sheet likewise improves. Liquid fuels can, however, also be produced using renewable means. Currently, field crops are used, but in the future, it will be possible to extract biodiesel, as it is known, from any plant material, such as wood residue, straw, or grass and tree cuttings. This will cancel out the vehicle emissions, although some CO2 will still be generated as a result of cultivation, extraction, and manufacture. Let us now consider the principal characteristics of hybrid vehicles. Hybrid vehicles have at least two drive units: a combustion engine and an electric motor, which is integrated into the transmission on this model. Engine and motor can each be deployed on their own or in unison with one another in order to optimize operation in terms of energy consumption. When kinetic energy is released, for instance, while driving downhill or braking, i.e. with the engine in overrun mode, the electric motor acts as a generator. The electrical energy is stored in a battery. This process is known as recuperation. When accelerating or at full throttle, the released energy can be reused. The electric motor helps the combustion engine to power the vehicle. The principal fuel saving of hybrid drives stems from this ability to balance out overrun and load phases by means of a battery. Ideally, the battery will be approximately half charged to leave capacity for both increasing and decreasing the charge. In order to achieve this, the battery is either charged during regular vehicle operation with the aid of the combustion engine or discharged during semi-electric operation. Move the cursor over the diagram to display the principal components. The advantages of the hybrid drive are lower fuel consumption, resulting in lower CO2 emissions too. Besides this, there is a further plus point too, namely increased torque. As you will find out in Chapter 5, electric motors, unlike combustion engines, generate their maximum torque from stationary. So not only is environmental compatibility increased, driving pleasure is boosted too. This comes at the expense of a number of drawbacks, however. Increased technical complexity resulting from the two drive types, combustion engine and electric motor. A higher weight due to the additional components, as well as the resulting increase in costs. The pros and cons of the various drive setups need to be weighed up carefully to evaluate the impact on fuel consumption and CO2 emissions. A vehicle which is predominantly driven in city traffic, stopping and accelerating frequently, can benefit from a hybrid drive system. However, a vehicle which is largely driven at a constant speed over long distances should not be burdened by the extra weight of the hybrid drive technology. In this case, a modern diesel engine proves to be more efficient. Now let's take a look at the fuel cell drive. Hydrogen, which is stored in compressed gas tanks, reacts with oxygen from the atmosphere to generate electrical energy in the fuel cell, which is in turn used to feed the electric motor. In overrun situations, this electric motor is also able to function as a generator and convert kinetic energy into electrical energy. Consequently, a battery is also required in order to store the electrical power generated during overrun phases, or put it on tap again for peak load phases. Move the cursor over the diagram to display the various components. The principal benefits of the fuel cell drive include the low energy consumption, as the fuel cell and electric motor convert energy more efficiently than any combustion engine is capable of doing. Absolutely no CO2 emissions at the vehicle. Only the water produced by the chemical reaction is emitted from the exhaust. Low noise emissions from the fans and the hum of the electric motor. And finally, impressive vehicle performance, as the electric motor delivers a high torque from standstill. And what about the downside? The fuel cell drive still entails a great deal of technical effort. The fuel cell drive, together with all of the ancillary assemblies, is heavier than an equivalent combustion engine. The high manufacturing costs for the fuel cell and battery are another major factor. These should both become cheaper to make over the course of future development, however. A further challenge lies in store in areas that are outside Daimler AG's direct scope of influence. Hydrogen would have to be manufactured in far greater quantities for the fuel cell to become a widespread means of powering vehicles. This should furthermore be carried out in an environmentally friendly manner by employing renewable energy sources. Click on Extra Info for an overview of the different ways in which hydrogen can be produced. Hydrogen can be manufactured by chemical means. It accumulates during iron smelting, for example, when iron ore, coal and water are heated in the blast furnace. Natural gas can also be steam reformed, a process which produces hydrogen and carbon dioxide. In both of these cases, however, fossil resources are used in the hydrogen's manufacture. and CO2 is given off. Hydrogen can also be obtained from the electrolysis of water. In this instance, the consumption of resources and CO2 emissions depend on how the electricity is generated. Biological manufacture is likewise possible, using biomass, for example, and steam reforming of the generated biomass. Research is also currently being carried out into the possibility of manufacturing hydrogen directly from special algae. Here, the environmental balance sheet depends on the cultivation concept used. In the case of sustainable cultivation, no consumption of resources takes place, as the hydrogen production process only releases as much CO2 as was previously absorbed by the plants. To make vehicles with fuel cell drives a viable alternative, a supply of hydrogen fuel also has to be made available. This requires special pipelines, tanker vessels, tanker trucks, and fuel dispensers. Currently, there is only a small number of hydrogen filling stations in the main metropolitan areas, of which only a handful stock compressed hydrogen at 700 bar, as favoured by Daimler AG. Their number must increase dramatically before fuel cell-powered vehicles become an attractive option for customers. Daimler AG is collaborating with the relevant fuel producers in all of the areas just discussed. An electric vehicle is fitted with an electric drive motor, just like on a fuel cell vehicle. But there is no hydrogen tank or fuel cell. Here, the electrical power originates from a battery. This is larger than that found on a hybrid or fuel cell vehicle, however. After all, it has to store the entire drive energy and not just surplus energy for load peaks. This energy is then dispensed to the electric motor via the onboard power electronics. The electric vehicle's battery is charged from the main supply. Move the cursor over the diagram to display the various components. The advantages of electric vehicles are similar to those of fuel cell vehicles. Zero CO2 emissions at the vehicle, low noise emissions, plus high torque delivery from a standstill. Energy consumption is even more efficient than in a fuel cell vehicle, because the power does not have to be generated in the fuel cell first. Instead, it is drawn straight from the battery. Countering these benefits are the by now familiar disadvantages: a high weight resulting from the heavy battery, and the accompanying costs which continue to be high. A further drawback is the short vehicle range at the present time, as the battery can only store a limited amount of energy. Today's battery technology is only suitable for compact cars, and even then for no more than the short everyday journeys. Only compact cars can be plugged into a standard domestic power socket and recharged in a reasonable period of time, for example overnight, whilst at work or at a park and charge station whilst doing the shopping. A new infrastructure would be needed to allow rapid charging of large vehicles within a matter of minutes, i.e., in a comparable time to that required for refueling. Daimler AG is pursuing all of the possibilities just outlined. The following models are already on the market, are currently being tested in fleet trials, or will be brought out between now and 2010. Various hybrid drives in smart and Mercedes Benz passenger car, van, truck and bus models. Fuel cell drive in the B-class as well as in vans and buses. And electric drives in the smart and the future B-class. The alternative drives also undergo ongoing development in research vehicles and studies. Can you recognize the alternative drives shown here? Label the vehicles correctly by dragging the matching descriptions to them. Then click on OK. Excellent. The hybrid vehicle can be recognized from the cylinders of the combustion engine. The other models have just an electric motor. This is fed by the battery alone on the electric vehicle and primarily by the hydrogen-powered fuel cells on the fuel cell vehicle. What are the pros and cons of alternative drive systems? Drag the descriptions into the columns as appropriate. Then click on OK. Well done. Alternative drives have many advantages in their favour, particularly where energy consumption, CO2 emissions and noise emissions are concerned. On the negative side is their weight, which continues to be higher, and the costs involved. New components are encountered in vehicles powered by alternative drive systems. The fuel cell, a traction battery, and an electric motor. The pages that follow give you a general idea of the basic workings of these new components. The chapter starts with a look at the fuel cell. Fuel cells convert hydrogen and oxygen into water. At the same time, the chemical energy released by this process is not dissipated as heat, as it is with combustion, but transformed directly into electrical power instead. The hydrogen is taken from the compressed gas tank and fed into the channels of one of the electrodes. A blower directs ambient air with the oxygen it contains into the channels of the other electrode. The sole product of the reaction is water. The air's nitrogen content passes through the fuel cell unchanged. The low operating temperature means that, unlike in combustion engines, no nitrogen oxides are produced. The transformation in the fuel cells takes place in a number of steps, as follows. The hydrogen molecules are split into hydrogen ions and electrons at the catalyst on the electrode. The electrons flow through the external circuit, serving, amongst other things, to power the vehicle. At the other electrode, the oxygen molecules are split at the catalyst and bond with the electrons to form oxygen ions. The hydrogen ions diffuse through the membrane. The special membrane can only be permeated by the ions and not by molecules or electrons. The hydrogen ions and oxygen ions join to produce water, which is then discharged. One single fuel cell supplies a voltage of around 1 volt. By connecting lots of fuel cells in series to form a stack, the voltage is multiplied accordingly. In this way, outputs of several hundred volts can be achieved, which can then be used as a source of propulsive power. What benefits does the fuel cell have to offer? Well, the reaction is a cold electrochemical one and not thermal in nature. The principle of thermal transformations, such as those that take place in internal combustion engines, means that losses are unavoidable. Not in the fuel cell, though. Consequently, its efficiency ratio is really high and currently lies at around 60%. There are no harmful exhaust gases. The only emission produced by the fuel cell is water or water vapor. The only noise is that made by the blowers propelling the gases. The fuel cell furthermore has no moving parts, meaning there is zero mechanical wear. The only wear is that resulting from gaseous catalyst poisons, which is why these have to be regularly rinsed out. If you would like to discover what the fundamental difference is between an electrochemical and a thermal reaction, click on Extra Info. On thermal motors, which include combustion engines, the degree of efficiency depends on the difference between the highest and lowest temperatures in the process. This is the theoretical limit, which is never actually attained in practice, however. Realistic efficiencies are 35% for diesel engines and 30% for petrol engines. The remainder is lost in the form of heat. A fuel cell, on the other hand, has a theoretical efficiency of 100%, although this drops as the temperature rises. 60% is achieved in practice. The aim is to reach 85%. The fuel cell works, as has been demonstrated by several generations of prototype vehicles from Daimler AG. Besides this, no other manufacturer has such a large fleet of test vehicles in customer hands. Nevertheless, a number of challenges still need to be overcome before series production can start. At the present time, a fuel cell drive would still be expensive for the private end user. Costs have already fallen substantially over the course of development to date, though. If this trend continues, a fuel cell vehicle could become economically viable. The first generation of the fuel cell filled an entire van, the Neckar 1. Despite its higher power output, the current generation fits into the underfloor cavity of an A-class or B-class. Reducing the weight and space required is not just important for accommodating the technology in the vehicle, however, it is also the key to reducing costs. The current fleet of fuel cell-powered vehicles is being operated under the technical supervision of Daimler AG. In this way, the necessary experience can be amassed for achieving the level of durability and technical maturity that will allow the vehicles to be fully entrusted to customers. Move the cursor over the vehicles to display the technical details of the fuel cell systems and see just how much development has already progressed. On which operating principle is the fuel cell based? Click on the correct description. Well done. A cold reaction between hydrogen and oxygen in the air takes place in fuel cells, which generates the electrical power for the electric motor directly. What advantages does the fuel cell have? Click on the applicable answers. Well remembered. Actually, nearly all of the benefits shown apply to the fuel cell. The only drawback is that the materials, especially the platinum catalyst, are unfortunately expensive. The batteries used in alternative drive systems are subject to a quite different set of demands than conventional starter batteries. After all, they have to do far more than just start the engine. A traction battery must be capable of storing larger quantities of energy and delivering an electrical output that is many times higher. The specific requirements vary depending on whether the battery is acting as an aid to the combustion engine or the fuel cell, or actually serving as the sole energy source for the electric drive. Batteries for alternative drives also have to be rechargeable. The batteries used, therefore, are storage batteries. The cycle number indicates how many times the battery can be fully charged and discharged before it can no longer be used for the intended application. Today's traction batteries manage up to 1,000 complete charge and discharge cycles. Because the battery in hybrid vehicles is generally only partially charged, then immediately recharged, the cycle number is much larger. This is sufficient to safeguard operability throughout the average vehicle service life. Self-discharge of batteries is a particularly important consideration in the case of electric vehicles. Even when it is not in use, a battery loses energy due to internal chemical processes. Depending on the battery system, as well as the age and temperature of the battery, self-discharge varies between a few % and complete discharge in 1 month. Another key variable is the energy density of batteries. This refers to the energy in watt-hours per kilogram of battery. Sometimes, the energy is also stated in reference to the volume if the space required is a decisive factor. The higher the energy density, the further the car can drive on electrical power for a given battery weight. Or, expressed in different terms, the higher the energy density, the lighter the battery can be for a given electrical range. The energy density of batteries is low compared to other energy storage media. It is only 1/100th that of petrol, for instance. Development is not standing still, however, as you can observe from the following comparison of different battery types. The lead-acid battery has been successfully used as a starter battery for many decades now. This is where its advantages lie: the proven technology and the cost-effective production. It is ill-suited to use as a battery in alternative drive systems, however, as its energy density is low, and the electrodes suffer from mechanical instability when the battery is completely discharged. The only application is in micro-hybrid vehicles, where a more robust version, known as an absorbent glass mat or AGM battery, is used. This battery is able to withstand the typical charging and discharging processes of this hybrid type. You can find out more about the various hybrid types in Part 2 of this CBT series. The nickel-metal hydride battery, or NIMH battery for short, is suitable for use as a buffer battery in hybrid vehicles. It offers the following advantages. The technology is robust, being the same as that used in many battery-powered appliances, and its energy density is superior to that of lead-acid batteries. On the downside are the high self-discharge rate, especially when fully charged, and the low number of cycles if left to fully discharge over a longer period of time. There is also the nickel-cadmium battery, a close relation with only slightly different properties that is described in the Extra Info section. The nickel-cadmium battery was a precursor to the nickel-metal hydride battery. Its properties are similar, but it is more robust, particularly in terms of its resilience to total discharging, which is why it is used in electric vehicles. It has other drawbacks, however. The memory effect, as it is known, reduces the energy storage capacity if the battery is recharged when it has only been partially discharged. As this is the case virtually constantly in hybrid vehicles, this battery is not suitable for such applications. It contains highly toxic cadmium. This metal is now prohibited in domestic batteries. Due to the 100% recycling process, however, an exception is made for industrial applications, particularly when used as a traction battery in alternative drive systems. The high-temperature Zebra battery possesses a whole series of ideal characteristics. It has a very high energy density, can withstand a high number of cycles, and has a negligible rate of self-discharge. It also contains no toxic or rare and therefore expensive materials. At first glance, it would therefore seem to be the ideal solution for alternative drive systems, especially in electric vehicles. Smelts of sodium and nickel chloride salts are used as electrodes. These have to be heated up to temperatures of between 280 and 350 degrees centigrade to allow them to absorb and discharge electricity. And this is where the major drawback lies. The battery has to be thermally encapsulated to prevent excessive temperature losses. Some thermal release is unavoidable, meaning that the battery must be heated to maintain the correct temperature. This uses up a portion of the stored energy. If the battery was shut down, it would be electrochemically stable, but it would take a long time to heat up before being operable again. The alternative is to heat the battery from the main supply while the vehicle is not in operation. From an energy consumption point of view, this is only worthwhile for vehicles which are used frequently. Move the cursor over the battery to familiarize yourself with its constituent components. The various versions of the lithium-ion battery are currently deemed to be the most promising option for alternative drives. They offer the following advantages. The technology is a familiar one that is employed in notebook PCs and mobile phones. The lithium-ion battery has the highest energy density of all the battery systems considered here. It has a high cycle number and a very low self-discharge rate. Lithium batteries acquired a negative image, however. A small number of lithium polymer batteries fitted in notebooks were overcharged because of defective chargers and caught fire. Other variants of the lithium battery are earmarked for use in alternative drives at Daimler AG, however, namely the lithium-ion batteries, which are safer. Besides this, the cells are embedded in a gel, protecting them from shocks, and surrounded by a sturdy steel housing. In vehicles from Daimler AG, they are furthermore electronically monitored and also integrated into the air conditioning system circuit to keep them operating in an optimum temperature range at all times. If overheating should nevertheless occur, there is a vent opening for controlled reduction of the resulting pressure buildup. It is intended to use lithium-ion batteries as an energy storage medium in hybrid and fuel cell vehicles, as well as in electric vehicles. In addition to the battery safeguards, further safety measures are to be incorporated into the vehicle itself. For example, all high-voltage cables are color-coded so that they are unmistakable. The insulation of the cables and connectors provides complete protection against electric shocks. In addition to this, apart from the actual battery, all of the other high-voltage components, such as the cables, power electronics and electric motor, are de-energized when the ignition is off. And they are subject to permanent electronic monitoring when in operation. In the event of a short circuit or a possible malfunction, the supply of power from the battery is immediately cut off. The same is true when the safety system detects a collision via its crash sensors. Arrange these battery types according to their energy density. Drag the labels into the table as appropriate, then click on OK. You've been paying close attention. The familiar lead-acid battery has the lowest energy density, and the lithium-ion battery the highest. Which measures are being deployed by Daimler AG to make the lithium-ion battery suitable for use in motor vehicles? Click on the applicable measures. Precisely. Daimler AG is implementing a whole series of measures to offer its usual high standard of safety in conjunction with electrical energy storage media too. However, the decision to have a fire extinguisher fitted still rests with the customer. Electric motors for vehicle drive systems have nothing to do with the electric motors used for windscreen wipers or power windows. After all, they have to provide a major boost to the combustion engine in hybrid vehicles, or act as the sole source of drive power in fuel cell and electric vehicles. The motors in question are three-phase alternating current motors. The following looks at two types of these, the synchronous and the asynchronous motor. You are bound to be familiar with this type of torque diagram for combustion engines. Electric motors, on the other hand, are every drive system developer's dream, for they deliver their maximum torque when accelerating from stationary. This dispenses with the need for a starter, and as the electric motor generates high torque from a rotational speed of 0, there is no need for a friction or hydrodynamic clutch either. Electric motors operate over a large rotational speed range, meaning that a transmission is often not required. The motor's direction of rotation can be reversed electronically, eliminating the need for a reverse gear. The upshot of all this is a simple powertrain. The crucial factor from an energy point of view, however, is that electric motors can function as both motors and generators. This allows kinetic energy to be recovered in a process known as recuperation. Electric motors, furthermore, attain high efficiencies of as much as 90%. By way of comparison, the maximum efficiency ratio in practice of petrol engines is 30% and of diesel engines 35%. In other words, electric motors transform nearly all of the expended electrical energy into vehicle motion. Electric motors have a simple construction, comprising the fixed stator and the revolving rotor, the only moving part. The torque is produced by the interaction between the magnetic fields produced by stator and rotor. At least one of these two parts must be built using electromagnets. Here it is the stator. The rotor contains a permanent magnet. The motor is controlled by an electronic circuit known as the frequency inverter. This supplies three-phase alternating current to the windings of the stator. On the synchronous motor, there are several magnetic windings contained in the stator. At least 3, as illustrated here, although many more are used in practice. The windings are connected to the motor control unit. The rotor contains a permanent magnet. Now energize the stator's windings with three-phase current by dragging the slide control to the right. The rotor follows the stator's rotary magnetic field, turning synchronously with the rotating field. Keep changing the settings to see what happens. The following characteristics are typical of synchronous motors. Because the rotor follows the rotating field exactly at all times, the motor can be controlled precisely. The motor's efficiency is high, as the rotor's magnetic field does not have to be generated separately. In order to generate a powerful magnetic field, however, the rotor is not made from standard magnetite, but from a special alloy with stronger magnetization instead. This results in higher costs compared to the asynchronous motor described in the next section. This type of rotor is heavy too, meaning that the synchronous motor has a higher weight. Due to its precise controllability, the synchronous motor is particularly suitable for operating in unison with a combustion engine in hybrid vehicles. However, it is also employed as the sole drive unit in more recent fuel cell vehicles and electric vehicles. Like the synchronous motor, the asynchronous motor features a stator with several magnetic windings. The rotor consists of a cage made up of several bars, which are held together at their ends by short-circuit rings. The bars, together with the short-circuit rings, form enclosed conductor loops. As on the synchronous motor, the electromagnets on the asynchronous motor's stator are energized with three-phase alternating current. This again generates a rotating magnetic field. This induces an electrical current in the conductor loops. This current, in turn, now produces a magnetic field from the rotor, causing it to turn with the stator's rotating field. Depending on the load, the rotor lags behind the rotating field as it turns. When compared to the synchronous motor, both advantages and disadvantages emerge. The asynchronous motor is a robust, technically mature electric motor, which is widely used in industry. It can be temporarily overloaded by as much as 2.5 times the rated power output. Overloading is only restricted by the heat buildup in the windings. When subject to such high loads, the motor does become slower, but it does not come to a complete stop. As the rotor comprises nothing more than the light cage, the asynchronous motor weighs less than the synchronous motor. The disadvantage is the lower efficiency compared to the synchronous motor, particularly when starting up. This is because the rotor field needs to be generated first, making it impossible for the motor to respond spontaneously. Asynchronous motors have been used exclusively as robust electric drive units, both in some types of hybrid vehicle as well as in fuel cell and electric vehicles. Today, though, preference is given to the synchronous motor for passenger car applications. What advantages do electric motors have to offer compared to internal combustion engines? Click on the correct properties. Well done! Electric motors offer a host of benefits. The only thing they cannot do is replicate the customary engine sound, which is bound to be welcome news to anyone who lives on a busy road. Synchronous and asynchronous motors possess different properties. Match up the properties with the two motor types by dragging each of the properties into the appropriate column of the table. You've been paying close attention. To sum up, the asynchronous motor is a workhorse and the synchronous motor a racehorse. So it's little wonder that Daimler AG relies on asynchronous motors for commercial vehicle applications and synchronous motors for passenger cars.